Okay, now it's time to continue, and in these sessions we have 3 sessions. And the first one is industrial session, so we have 3 speakers from companies, and so we'll see how AI and the questions related to AI is working in industry. So the first speaker is Magnus Sundberg from Saab.
Thank you very much. It's interesting to be here amongst, I feel like a mouse among cats, but I'm going to give you a little bit on the industrial perspective of what I think that we might be able to use AI for. I'm also going to talk a little bit about digitalization and the consequences of that for Saab. I come from Saab surveillance, specifically the radar part. I think we're probably the part of Saab with least progress in AI. So bear with me, because there are many interesting applications going forward anyway. Just to give you a little bit reminder or information of what Saab is. Saab is a defense and security company, mainly based in Sweden, with a very diverse product portfolio. We have, I think you recognize many of these things. This is my home arena. We have the Global Eye airborne early warning radar, the Giraffe, which is my little baby. We have air traffic management. Of course, we have, as you know, the Gripen fighters. The Visby corvettes, so marine vessels for warfighting. Underwater systems. Since a few years back, we have also Kockums within Saab, who do the Swedish submarines. So it's a very, very diverse portfolio of high-tech equipment. Saab stands for Svenska Aeroplan Aktiebolaget, or Swedish Aeroplane Inc., if you wish. It started in 1937 as a handshake agreement between Mr. Wallenberg of the day and the Swedish Prime Minister in an effort to provide fighter planes for Sweden for the imminent threat of World War II. Everyone that could build planes needed them for themselves, so we had to try and build them for Sweden. It was at the time, or still is, a tremendous engineering effort. This is a picture from the engineering office. Become kilogram hunter, it says on the slogan here. So it took a lot of man hours to produce these planes. Last year, as you probably heard, Saab, together with Boeing, won the contract, the huge, I think it was $9 billion contract for the US government to provide them with trainers for training fighter pilots, initially at least in the US, but likely globally. And I think it's just awesome that such a small country as Sweden can be part of something as advanced as this. It took 3 years from more or less a clean sheet until this thing was flying. So I think it's a good example of how modern ways of working faster is also coming into our industry. We have also been working with radar for a very long time. This is, I think, probably the first one. Echo Radio from 1943 was a joint venture between various organizations. Then Ericsson took care of radar in Sweden for a very long time, and in 2006 we were bought by Saab. So now most of the Swedish radar efforts are done by Saab. Over the years, we've seen quite a big change in both in what we do and how we do it. We started out in the, well, essentially since World War II up until, say, the 80s or so, radar was composed of a relatively small number of very, very high-performing and customized components. Hence the vacuum tubes that was part of the name of my presentation. And nothing wrong with vacuum tubes or traveling wave tubes, fantastic pieces of physics, but with their limitations and not to mention their price. Over the years, we have migrated towards having, rather than a few very advanced components, we've migrated to having more and more little like individual radars. And all of our modern radar systems are what we call AESAs, actively electrically scanned arrays, containing more standardized product, and the digitalization has made these products become more and more sort of towards the software end. We also see a strong convergence in the microwave and electronics business, as you know. Previously, military industry was probably the technology driver in many fields, but now we are completely sort of overtaken by, for instance, telecom industry. I talked to an American guy representing a component manufacturer, I think it was Maycom. He mentioned that they had invested $100 million into one AD converter. I mean, or at least, or a family of AD converters. That's typically what we invest in a new radar generation. So there's no way to keep up with telecom and the civilian industry. When we build 5, they build 50 million. So, more and more industries, automotive, 5G, and so on, uses the same type of technology, which is beneficial for us, of course, but it also means that, as we will see later, there will be more and more collisions between our different branches. This has led up to what we nowadays refer to as software-defined radar. This is it's not a product, it's experimental platform that we run together with Chalmers and also with FOI, the Swedish Defense Research Agency. And what it is, it's essentially, it's a bunch of antenna, little individual antenna elements, all of these. Each of them has its own DA converter and AD converter. So it's the tremendous amount of hardware effort and refinement that we used to see is now reduced to an antenna with essentially 2 pieces of electronics. The rest of the radar is just software. Such a thing as this will produce in the order of a gigabyte of data per second per antenna element, and in a full-scale radar it will probably contain a couple of thousand elements. So we're talking about terabytes of data per second. Most of it is noise, but nonetheless. Which is in fact an interesting problem. I'll get back to that just in a bit. Traditionally, with radar development, most of our effort has been to try and see more and more things. Smaller things, now with stealth and all that, but also to see things further out. We used to do a lot of microwave engineering, a lot of power and cooling and mechanical design and whatnots in order to have the radar be able to see more and more. And this is a recording from our Kallebäck office for, I don't know, 5 minutes or 2 minutes or something. You can see something's flying out here. And which is also quite obvious in these pictures. Most of what we see is quite uninteresting. What we want to do is to bring order to this mess, to create some sort of situational awareness. And I think that is where now the mathematical parts, the signal processing, the software, the AI perhaps, comes in to take all that raw data and figure out what is actually out there. So the blue ones are aircraft, these ones are probably birds, drones, whatnots. But anyway, with a much better structure than before. One significant problem lately in society that I'm sure you're aware of, you know, the Heathrow and Gatwick incidents in the fall or early winter, with sorting out drones approaching Heathrow Airport. That's a big problem for radar, because when we allow the radar to see objects as small as drones, we will inevitably also sort of invite birds to appear. And we have, typically with a radar, we can see maybe 1,000 birds or 2,000 birds all the time, and perhaps among those one or two, hopefully 0 drones that in very many ways behaves just like the birds. This is a short 1-minute film about that problem.
Drones, or UAVs, are an evolving threat to airports throughout the world. Since these UAVs are small and fly both low and slow, it's a challenge to distinguish them from their surroundings, for example, a flock of birds. That's where the giraffe ELSS function, enhance low, slow and small, makes a difference. The giraffe ELSS function gives a unique ability to detect, identify and track any UAV, and even single them out in a flock of birds. Giraffe ELSS detects, identify and track any UAV.
I'm sorry for the sales pitch, but it was the animation I had at hand. An interesting thing with it, the functionality that we have built, maybe it counts as AI, but it's certainly not machine learning. So it's more or less handcrafted code that we have invested thousands and thousands of man-hours into getting a very high classification probability. An interesting thing that has a take on AI perhaps is how do we keep ahead of the drones when they evolve? This is a picture from an Icelandic researcher I happen to know. He's working on flapping flight. I don't know why, but he is. There are several, you've probably seen them on YouTube also, various mechanical birds that flies as a bird. And in the future, how do we distinguish this thing from birds? That one is easy. That's an octocopter. But these ones are more tricky. So I think we have to realize that our radar systems has to be able to adapt to change. We cannot just build them once, ship them to the customer, and there they are for 40 years, as we have traditionally done. The systems must evolve. So a little bit jokingly, I would like to come to this point that we can say that I have a well-trained radar for sale with 10,000 hours of experience. The system itself must somehow be able to gather experience and adapt to changing conditions. And we are actually having a couple of thesis projects on this going on for both target behavioral analysis, but also for the radar signal processing part of this. Another application of AI that relates to big data, this is from a joint venture that Saab has between us and Digital Globe. We collect 240,000 square kilometers per day of half-meter resolution data. So there's plenty of data to play around with. And then that data is interpreted, as in the rightmost picture here, into a 3D mapping of the planet. It's used, for instance, for navigation purposes. For the radar, we look at this. Saab has been opting to classify these images using AI into mappings of the terrain type. And that will enable us to have, say, autonomous vehicles navigating through terrain. You have to know if it's a swamp you're driving into, or it's a desert, or whatever it is. And here I think we actually do have a WASP PhD student active. Another topic that relates to AI is something called cognitive radar. Normally, radar does whatever it's pre-programmed to do, and then we do most, or if not all, of the advanced processing on the receive side. We have fairly sophisticated signal processing algorithms, but the transmission of the radar is pretty much pre-programmed and not adaptive to change. With cognitive radar, the idea is to measure what is out there, for instance, jamming, either hostile jamming or intentional jamming, but also unintentional jamming just by conflict with, say, a telecom system, It could be clutter such as rain or traffic or whatever, and then to adapt how the radar not only receives and processes, but also how it transmits. So we will have something called adaptive waveform creation, then that the transmit signature of radar is adapted to the reality, or to whatever is necessary. We do this with FOI, but also in cooperation with Aalto University in Finland. And where there is cognitive radar, of course, there will be a cognitive adversary of that radar. So cognitive electronic warfare systems, this is something we're looking at in our site in Järfälla. An electronic warfare system is either something that is there to detect, say, a radar, to detect it, to identify it, and to tell where it is. But it can also be to try to jam the radar, to prevent it from doing its job. And of course, as the radar gets more and more agile and gets more and more, how should I say, unpredictable in how they operate, the electronic warfare systems has to keep up with that development then. And there is an interesting duel, I think. I wrote generative adversarial networks. I'm not quite sure that's the right term for it, but it's anyway here two AI-enabled systems that will compete with each other. So that'll be interesting to see how that turns out. On a completely different note, more from a sort of employer, perhaps, note, is what I call the commoditization of skills. So when our previous or older skills becomes less valued, for instance, with us, microwave technology has always been our most precious knowledge. Now with 5G, you will be able to buy much more of what we previously did. So there's no doubt that digitalization and AI turns these core disciplines into commodities, if you wish. So we will need new skill sets, and we must evolve even faster to keep up. But an interesting twist on that going forward, I mean, everyone is rushing to bring in AI to say that we have autonomous this and artificial that. But what will be the defining things going forward when everyone has that? Because we talked about our favorite enemy yesterday, Thales, for instance. Every radar provider, every provider of, well, every competitor will, of course, have AI wherever suitable in a couple of years, and probably in a few more places. When that becomes a commodity? When autonomy is no longer a selling point? What should our direction be then? I brought one little interesting, hopefully, or funny example of other type of skills that an industry might need also in the day of digitalization, and this is actually about cooling. This is a tokamak for what's it called, for nuclear fusion. Tokamak reactor. This thing produces roughly 20 megawatts per square meter in heat radiation. If you want to cool it, you have to be able to cope with that. This thing in the middle, the sun, produces around 60 megawatts per square meter, so it's a little bit more. And that one, this is a gallium nitride amplifier chip from an AISA radar. It produces 5 times more heat per unit area than the sun. So you can imagine the challenges in keeping a modern radar at full power cool. So there will be so many different things that will be necessities to be able to keep up. We have to have cool hardware to put the AI and the autonomy into going forward. And I think that will be a key to become, or to keep competitive. So to summarize, I think digitalization and AI and autonomy brings fantastic opportunity, but also, of course, challenges. Adaptive, cognitive, and learning systems are key in this rapidly changing world. And I think broad engineering skills will be essential for future competitiveness. So not just software. I try to summarize my message in building good system takes a lot of intelligence, some of it artificial. Okay, thank you.
Okay, we have time for one question or two. Maybe I can ask you one question about the production. So, as your production is not like in a big series, so does digitalization helps in improvement of efficiency in the development?
Yeah, absolutely. As I mentioned, this AD converter salesman I talked to, they invest what we reasonably can invest in a radar family. They invest in one circuit. So it brings in fantastic possibilities to make really much better equipment than we could have possibly funded for ourselves, for sure.
Okay, thank you very much.
Thank you.
And now we are moving from sky to the space. So we have a guest from RUAG, Markus Borsand.
Thank you. So first of all, I realized that I might have come up with the most complicated title of this seminar. So I will talk about human habitation beyond planet Earth enabled through highly reliable autonomous systems. And I want to start off where Magnus left, because I feel also like a mice among cats here. So because I'm an engineer, and I will give you more like an application examples of what we can use autonomous systems and AI for, to give you some inspiration perhaps also for the future. So first a little bit about RUAG Space. I will not run a company presentation here. This is the only slide you will see about RUAG Space. But some of you are probably not familiar with who we are. But we used to be Saab Ericsson Space. And we are still up in Delkomotet, close to where Magnus is. And we are a space company. And we deliver products in order to implement space missions. We don't develop launchers or satellites ourselves. Our primary product is this kind of onboard computer where you implement the autonomy on board a satellite or a launcher. So this is like our bread and butter type of products that we have. This is our everyday life. Everything we do ends up in space, realizing various space missions, ranging from, as I said, typical satellites, the launchers that takes the satellites up into space, to more complex things like this is a robotic arm for the International Space Station. Our missions are from a few years in low Earth orbit, so fairly close to Earth, up to the 15 years in geostationary orbit, where typical telecom satellites, television satellites are in orbit, up to our oldest mission of today is a 22 years deep space mission studying the sun. And our products, I think they look fairly boring. It's typically a computer looks like this. This is a computer for a Mars rover that I will show a little bit more about. This is a computer board. So the products as such are not so fascinating. It's more the application that makes it fascinating. And the application I will talk a little bit more about is what we are working on now, and that is to put humans on Mars. And in order to do that, autonomy, autonomous system, and AI are essential components. And you can, of course, ask yourself, why should we go to Mars? And I think that this is something that is in our blood. We as human beings, we are explorers. We want to go beyond the current borders. We want to see what's out there. That is something that we have always had in our brains or in our hearts or so. And I think you as researchers, you have that in you. But this is more a project for the human mankind, to put man on Mars. And I will tell you a little bit more about how to do that. So this is where we are today. The plan exists. Today we have the Earth and we have a space station surrounding or orbiting our Earth today. It's fairly easily accessible. It takes a few hours to go there. Technology exists. It's a huge structure orbiting the Earth. But in order to go to Mars, we need a second version of that will reside in the so-called cislunar space, so the space between the Moon and the Earth. And in principle, in order to go to Mars, we need this kind of thing because it will act like a gas station in space. There will be a space station here into which we can send supplies, such that once we send humans on their journey towards Mars, they can stay here at this lunar gateway and tank up with supplies and so on before they go to Mars, because it's too complicated to bring all the supplies from Earth with one spaceship because of the gravity of Earth. You would need such an enormous rocket in order to go or leave the Earth gravity. So that is out of the option. Instead, there will be a tank station out here between Earth and the Moon. And then finally, we can go to Mars. But it's quite a long journey. One-way ticket is 1 to 2 years, depending on how Earth and Mars are related to each other. But it's doable. It's not fantastic technology that is needed. We could do it today. But before going there, we use this kind of robots that we send to Mars as pathfinders. And they have 3 very important objectives. First of all, we send these robots before we send humans in order to minimize risks. Instead of endangering human lives, we send robots there to explore the planet. But also, we send them there in order to understand that or prepare for humans returning from Mars, so that they don't bring back dangerous biohazards or so that could pollute our environment and kill humans back on the Earth. And we also have them there in order to find resources that we can use on Mars, like water. Instead of having to send all the water that humans living on Mars needs there, we are trying to find the resources and use them on the planet instead of sending them from Earth. And there is a program, there is a number of drones already available on the Mars soil. Europe has one where we are heavily involved, called the ExoMars Rover. It will be launched in 2020 and reach Mars in 2021. And this is a picture of it. So this is technology that we have today, and this kind of rover that we have here, it is not very capable. It can drive around on the Mars planet, but it cannot take decisions of its own. It's all pre-programmed what it do, and it's being instructed from Earth, not movement by movement, but more execute sequence X, execute sequence Y. So it's not super intelligent, but that is what we can do with today's technology. And today's technology, we are limited when we develop space technology, and our primary limitation or challenge that we have to overcome is radiation. We cannot use all the modern fantastic components that like telecom industry is producing for us, because they will not survive more than perhaps a month in space environment. They will die due to the radiation primarily generated by the sun. So we have to use radiation hard or radiation tolerant special components into which a component supplier is not willing to invest 100 millions in developing, because here we are not talking about 5 systems, but 1 system. So the number of components or types of components that we have available is very limited. We have to deal with what is available, and that limits also the capabilities of the autonomous systems that we can realize by typical engineering skills. We also use fault detection, recovery, and isolation principles so that our systems can recover from failures, because failures happen in space. So this is perhaps the most, or this is where the focus of autonomy is with today's systems, that they can recover from failures. We also have the problem with operating temperature. We operate in vacuum. We have to cool our systems purely by cooling it with metals and so on. We cannot use air or so to cool down our chips. As you must realize, it's fairly hard to repair the stuff that we send up into space. I say it's difficult. There are ideas of how to repair things in space, also when they are quite far away from Earth, but it's going to be super expensive to do that. So we use a lot of extensive testing before launch and have to come up with a lot of corner cases and test for the most difficult cases our products can ever experience. And then we have the thing with the huge distances. So we have communication delays. Just consider that sending a signal from Earth to Moon takes 1.3 seconds. Perhaps that is okay to sit with a joystick on Earth and command a Rover or so with a 1.3 second delay. But doing it with Mars, where the one-way communication varies between 3 to 21 minutes, then it's not an option to have a human there driving around the rover. It has to take its decision by its own in order to explore the planet. So, technology of today, this is just a typical picture of how an autonomous Mars rover is built up. You have a computer delivered by us, has a nominal and redundant part. The redundant computer can always take over if the nominal computer fails. There is a third computer in the system, a navigation computer that takes input from a lot of sensors, primarily cameras. And the computer generates stimulus to the actuators like the wheels, or it could be a drill or so. And you have a lot of sensors in the rover to detect temperatures and that kind of stuff. Not super complicated. It has been done before. The things that are special here is this failure detection, isolation, and recovery that we implement like in a supervisor function that is completely independent from the computers that does the normal execution of the system and handles the autonomy and so on. This is the actual picture from the 2020 ExoMars rover computer. And you can also look upon it like this. It's not very exciting. Just to give you some key performance figure here, the CPU, or the processing power here, it's 80 dry MIPS. So 80 million instructions per second. That is nothing today. I mean, I don't know what to compare with. What kind of computer is that? When did we have this kind of performance in our ordinary day life in computers and so on? I think you have to step back like 15 years or so when the laptops had this kind of performance. But this is state of the art when it comes to space electronics. And that of course limits what you can do from an autonomy and AI perspective. But the computer as such is super reliable. You have a reliability figure down here. I could add more 9s, but I stopped with 4. I think that was enough. You also have low power consumption because current or power is a source that is very limited when it comes to this type of system. But you have a very low and modest processing performance. Now, to go from here to the next step, to realize this type of mission, you need something completely else. So look at this movie first.
The planet Mars has been mysterious for centuries. But over the past few decades, a fleet of orbiting and landed spacecraft has greatly advanced our understanding of it. Based on this knowledge, Mars scientists are now ready to take the next big step, bringing Martian samples back to Earth, where the full power of our terrestrial laboratories could be applied to unlocking the story of the red planet's geology, climate, and especially its potential for life, either in the past or even today. But however you tackle it, returning samples from Mars is definitely a complicated problem. So how could we actually get a sample from Mars? One approach is to use a series of 3 spacecraft working together like a relay team to deliver samples to Earth. NASA's next Mars rover, currently in development, planned for launch in 2020, will acquire a set of carefully selected samples of rocks and surface material and store them in sealed tubes for possible return to Earth. NASA and the European Space Agency are now working together to explore options for a pair of missions that could take the next steps to bring these samples back. In one scenario, after the Mars 2020 rover has placed its collected samples on the Martian surface, a second follow-on mission would land nearby, deploy a small rover to fetch the samples, and bring them back to the lander, where they would be loaded into a container and placed atop a small rocket. The rocket would then lift off, carrying the samples up into Mars orbit. Waiting in orbit would be a third spacecraft, an Earth return orbiter, that would find the samples in space, catch up with them, capture the container, and bring it back to Earth. With Mars samples safely back on Earth, scientists around the world would be able to study them in state-of-the-art laboratories for decades to come. The payoff of a sample return would be a breakthrough in our understanding of the history of Mars and of the potential for life beyond our home planet.
Okay, so this is what we're working on, but with our current rover technology, we cannot realize that type of mission. So in principle, what we are lacking or our challenges is, of course, this delay in transmission between Mars and Earth, 3 to 21 minutes. So this type of rover, we cannot control it from Earth in order to make it collect the samples and then go back to the launcher again. It has to be done autonomously. So it's a quite complex task that we are trying to implement, and we need higher degree of autonomy and AI in order to realize that. Our main challenge there to do that is that we have to improve our onboard computer performance from 80 drive MIPS up to more than 10,000 drive MIPS. But this is just, I would say, an engineering problem, so we will solve that. But we will also need highly reliable navigation and fetch algorithm that will be implemented in this onboard computer in order to be able to realize a mission like this. And this is where you come into play to be able to take part of that and help us in industry develop those kind of AI algorithms. So just a summary, exploration of space by humans will in the next decades become a reality. I'm 100% convinced of that. The human exploration of space requires continuous development of autonomous systems. Robots are forerunners before sending humans deeper into our solar systems. And the robots and the rovers are built using these kind of standard space technologies where radiation effects and mitigation, where we work with mitigation through failure detection, recovery and isolation, that limits the kind of performance or so that we can actually realize. But with the new developments that we're doing, we will provide the computational performance needed. But the only way to realize these kind of future missions, and they are not, this is not science fiction, they are 10 years away, these type of missions. So in order to realize them, we need to make more performant processors available that can survive in deep space. And this is the key in order to also implement more advanced autonomous algorithms and also AI algorithms in space. So thank you very much.
Okay, a question?
You can ask a naive question. It's a naive question. Why do you need special electronics? Why not just shield the electronics?
You could shield. That is the Russian approach. That's how they have always done it. And the disadvantage is, of course, that then the mass goes up. And the mass or the weight of the systems that we launch into space, that is a super limiting factor, because that means that we need to have more performant launchers. And so we're limited, let's say, with respect to launcher performance into what we can launch into space. So shielding can be done. We're working with that with a mission going to Jupiter, where the radiation is even more severe than on Mars, where we use shielding. But it's a complement to this kind of radiation-tolerant components.
Can I ask you, I have seen many pictures here you have from NASA and ESA.
Yeah.
Does it mean that you are cooperating with them?
Yeah, that's a good question. I mean, running space projects is more or less always an international cooperation. We as Sweden have very few space activities ourselves. We do most of our space activities and space research in cooperation with ESA. And ESA is also cooperating with NASA. So working in space is always a big cooperation. That's how it works. Yeah.
Okay, thank you very much. Okay, now we are going back to the Earth, and we communicate. So now it's from Ericsson, Ulla Angelsmark.
Indeed. From the possibilities of air and space into the claustrophobic setting of factories and data centers. So I'm Ulla Angelsmark. I'm from Ericsson Research area Cloud Systems and Platforms, where I've been working with distributed systems, industrial IT, and industrial cloud for these past 5 years. And I will give you a little bit of insight tying back to what Jan Bosch spoke about earlier today, about the problems before you get to the artificial intelligence, before you can apply your algorithms. So data collection. I had a couple of different subtitles I've been pondering. There was, you had, okay, data collection, not as easy as it looks. We got data collection from the trenches. When theory hits reality, there will be bruising. We've had a couple of ideas tossed around, and this one summarizes it pretty well. Just a quick overview about what we'll be talking about today. The introduction more or less done. I will introduce the 5G-enabled manufacturing project, which is where I've been doing most of my work these past few years. Some of the backgrounds and the goal. We'll have a look at the data center and the factory we've been working with, see what goes where. I'll mention some of the problems that we've encountered, the challenges, the solutions, and when we couldn't find solutions, just the workarounds. Summarize, and if there's time left for a bit of Q&A, I'll try to answer any questions you might have. So, 5G-enabled manufacturing. It's a Vinnova-funded project that's been running for since December 2015, with the sort of the underlying idea to what would happen if we just connect everything in a factory using the latest in wireless, cellular, even 5G technology, and try to sort of enable all the possibilities that would come from this. The project started with 3 partners, Ericsson, SKF, and Chalmers. Now we've moved into the second phase where we added Siemens and Volvo, and hopefully it will be even more interesting to see what they've come up with. It should be said that this whole presentation is from my point of view. It's from the data collections sort of viewpoint. I have not personally been involved in the cellular network, and I have not been working with the artificial intelligence people, their algorithms. I've just sort of been the middleman between the data and the algorithms. Much of the work has been focusing around these 4 demonstrators. So we have the factory radio design, which is basically providing the underlying infrastructure, making sure that everything is connected and everything can talk to each other. Then we move over to the stationary equipment connectivity, where we sort of connect all the machines using this infrastructure. We get the data, the parameters from the machines, we connect other sensors, we read the sensor values, and we make sure that it's available. In the end, for machine health assessment and predictive maintenance, eventually. But we have some ways to go before we get there. The network and cloud part is then connecting the factory to the cloud, of course. We also have the edge connectivity. We have a cellular network in the factory connected to an edge cloud, so to say, where we have services. We need to design the services. We have to get the architecture in place, look at what kind of storage we need, make sure there's software needed for the analysis and analytics, database services, and all that. And finally, we have the mobile connectivity, which is basically making the data available for the people on the factory floor, so that the personnel, the maintenance crew, and the service personnel can bring up their handhelds, look in an app, and see, oh, this machine looks a bit funky. I think I can go over there and see if it needs some repair. And this is where I came in. So this was a couple of months after the project started. We had the factory, of course, was up and running. It's a real factory, so it's no experimental setting, which we'll come back to later. We have all the machines connected. We have the edge compute in the factory. We have a massive data center in Lund, and we have some data scientists and researchers eagerly awaiting the data. So, what we do with this? Well, first of all, this is what it actually looks like. There is something really there. We have a, let's see if this works. Up there we have the robot. this particular robot, it's working in a grinding machine. So it picks up those black rings over there, puts them in the grinder, well, they get a bit of polish, a shine, and then they go out on the lower pallet off to the next step of the assembly. These here radio dots are antennae located throughout the factory, and they are in turn connected to this flight rack, which is basically a stripped-down version of a base station that you will find in any cellular tower. This is an early prototype, which is now actually, I think it's actually in production for private LTE networks. This is then connected to the data center we have in Lund with massive amounts of compute and storage. So all the pieces up there, now we have to sort of work the software to make them work together. But of course, it's not without its problems. We encountered quite a bit of challenges here. The first, well, ties in rather nicely with the space exploration. The equipment was not under our control, although we could actually call up someone to have a look at it, which is probably not possible in space. But we discovered this early, quite early. Even just a couple of weeks into the project, we stopped getting data. There was no connectivity to the machine for whatever reason. I called up a guy, my contact, asked him to have a look. He went out, and well, the machine was the router was gone. Someone had tidied it up. Maybe it fell down, and someone tossed it. These are things that you encounter out in the real world. So what we had to do is we had to get a new router there, and then it became sort of painfully obvious that that's not the way to do it. That we go there, we bring our new router, we go into the room where it's supposed to be, and we place it. Because it took, I think, 2 or 3 weeks just to arrange all the people necessary to get the keys and escort us there, and then. So you need friends in the factory that can help you out. That goes to the next sort of issue here. The factory and the factory personnel, they're committed to production. They cannot drop anything, just leave it there and go help with your problems. So, for instance, we had this issue with one of the onboard software in one of the machines. It was a bit dodgy. Every now and then it would stop sending data for no reason. No error messages, everything looked fine, but no data coming. Turns out there was an upgrade available, but it would require shutting down the machine, doing the upgrade, making sure it worked, then bring it back up. A couple of hours, maybe a few days lost production. Not going to happen. This had to be scheduled with normal maintenance. So once, twice a year, tops, that you could sort of do these requests. The third one is more related to the actual problem at hand. The data collected, change it continuously. As the automation experts and the data scientists meet, they discuss what data they need, what kind of new sensors they need to install, what kind of parameters they should read, what to do with it. Someone had to implement all that. Someone had to make sure that we got the data from the new sensor, we put it on the same format as the other data we had, it was sent to the same database, and it could be read similar to all the other data. So it's basically you have to ensure that you use standards and open source as much as possible, because especially for projects that are let's say sparsely resourced. It was basically me. You need to sort of make your life easy. This one here, one of the more interesting ones, since we are Ericsson. The connectivity cannot always be trusted. This particular picture is from an interesting incident we had where a rat ate a piece of the fiber cable. And apparently, the ISP that we were using at the time could tell there is a break, it's about a couple of 100 meters in some direction, but they couldn't tell which direction. So it took a fair bit of time to find that problem. Another time, it was for some reason again, we just lost all the connectivity in the factory. Nothing worked anymore, and it turns out that one of the original engineers that had installed the Ericsson software had entered the expiration date of the software licenses to the end of the project. And most people here know that Vinnova projects never stop on the date that you first set. It's always a couple of months later. That also took some time to discover. Here's then what we ended up with. Once all the details were hammered out, we have the factory over there. We have the ingest workers, which are basically small processes running out on the edge, collecting data from machines or collecting data from a certain set of parameters that they are in charge of. We have a local streaming framework. Since we cannot trust the connectivity outside, we need to have a local buffering in order to make sure that we don't lose data needlessly. Over here, we have the sort of global streaming framework in preparation for the time when we scale out and get more factories and more machines. And of course, this permanent storage. And finally, the analysts could get something to work with. And since one of the hard-earned sort of lessons was that we can't really trust anything, we monitor everything. We monitor the links to the machines, the links to the ingest workers, the links between the data center, both from local and global, in order to make sure that everything is up and running at all times. And if you see here, I missed one. That one came back to bite me. After an upgrade in the data center, one of the database services lost its IP address, and no data was collected for that week before I discovered it. So each of these, when there is an alarm, first, if I have a rough idea of how to fix it, it could be basically turning it off and on again. Bring down the process, bring it up. Maybe reconnect, maybe resubscribe. If that doesn't work, I get a text message in order to have a look at it. And if I can figure out what the problem is, I try to implement it so that next time I won't have to do it manually. Basically, automation is the key here. To summarize, data collection is actually a lot harder than it looks. So when you get, as a data scientist, or if you're working with any amount of big data, even though not necessarily digging through rat's brains to get it, sometimes there is a lot of work in order to get that nicely formatted, streamlined data. If it can go wrong, if there is even a remote possibility that something in the data collection process can go wrong, make sure that you monitor it and try to remedy it as soon as you can, or as automatically as you can. And there is one missing here that I forgot to mention, or I think I brought it up earlier. Make friends with the people on site, so you have someone on call in case all hell breaks loose. And I think that was it. Yes, thank you.
Thank you very much. Okay, some questions? Look at your connection.
Thank you. So I'm curious, Ola, I mean, you did your PhD in theoretical computer science. We had the talk this morning about John Bosch. So I'm curious, can you relate? I mean, what's the difference between doing a PhD in theoretical computer science compared to the work that you do now?
I go through less pen and paper. No, there are more similarities than what you might think. There are things that come back to haunt you. Every now and then you encounter someone wants to do something that you actually, at the back of your head, you think, I know this. This can't possibly work. But then you have to go back and sort of look at the either NP complete list or even unsolvability of the problem. So that's always in the background. And then, of course, the attacking a problem is pretty much the same. I mean, you need to sort out the details. What do I know about this? Is there anyone I can ask that already knows the answer? Of course, when you're a PhD student, you don't have that luxury because that guy won't answer it. But anyway, I think that's, yes. What you learn is that, like I said, there will be bruising. Every now and then you will hit the wall, and you might hit it very hard. But if you have a sort of, you do your homework, and then it all works out, or not.
Can I ask you? You know that there is quite a lot of industry, like process industry, which collects a large amount of data, and
yes.
they are kind of reliable.
Yes.
And now we are talking about these problems. Is this other type of data or other type of communication? Why it comes this problem?
No, the thing. So the idea with this project was the 5G technology, going wireless. If you have a factory, it's normally quite a static setup. You have wires, you draw the wires, and you have the machines, and that's it. If you want to move it, it'll mean redrawing the wiring and making sure that everything is in place. So modern factories are moving more over to sort of a smaller batches. With we didn't talk about this here, but we have had a look at AGVs, autonomous guided vehicles, that sort of more or less autonomously move the items from one place to another to do their work. So these have to be wireless, of course. And there is also having the freedom of moving of the robots and the machines being more or less wireless. There are definite possibilities with that. Some of it is obvious, like the AGVs. Some of it probably won't become obvious until we have the technology. So one thing that we're looking at is the ultra-reliable connectivity that's being worked on in 5G, where it could be possible to move, say, even tight control loops from the machines. So the machines can be it can be dumb, they can be fairly straightforward, and move all the compute to the edge, have it in the factory.
Okay, thank you. So, thank you very much.
Okay, thank you.